Okay, good morning, everyone. Um, I'm good. How are you? You good? Okay, so I will go ahead and get started with today's lecture, which is still indeterminate system, but now we are adding to this indeterminate system more making more complex by adding gaps and thermal effects. So let me start first with this beam. Let me open this. Let me start first with this beam, and I do have a sun here. It's not like the best sun, but like it conveys the information. And I told you that this beam, initially it was at 0 Celsius, and then for some reason, the final temperature of this beam is 50 Celsius, as if like this beam was like in Canada in the morning, and then late at night I took it to Dubai. So it is like the final temperature is 50 Celsius. So now the question will be, what is the change in temperature that happened to that beam? Or is this beam, the temperature increased or decreased? It increased, right? So what we are interested in here, that we want to find the change in temperature that happened to that beam. So we want to say that temperature final minus temperature initial. And obviously we will say 50 Celsius minus 0, it is 50. Here's the question. So if the temperature increased, so will the beam expand or shrink? It's going to expand. So here's a good information to know, that the delta T has two options, either greater than 0 or less than 0. If it's greater than 0, then it's going to expand. If it's less than 0, it's going to shrink. This is a very important information. I know it's silly, but this is very important, just like to figure out this. And what we call delta T is, we call it, I would say, change in temperature. Or in that case, I'll be saying that this beam, the temperature increased by 50, for example. Okay? So let's go back to the beam a little bit, and then we will relate the delta T to this beam. So if I told you that this beam is made out of steel, and for all the materials, every material has something we call alpha, which is coefficient of thermal expansion. And the definition for this alpha is the amount of deformation per unit length and per unit temperature. So every material, and this is the table, what the table tells you, for example, steel has an alpha of 6.5 times 10 power negative 6, and the unit is 1 over Fahrenheit, or you can have a Celsius unit. So every unit here has an alpha. So 6.5 times 10 power negative 6 for steel, that means this is the amount of deformation if I have a unit length and if I have a unit temperature, okay? So if you know, for example, if this beam, the alpha is given, and now you already told me that the temperature increased by 50, so you all agreed that it's going to expand by delta, and this time we're going to go delta is delta T, which is delta temperature. From your understanding of what I mentioned this minute, like for the last 2 minutes, what do you think this delta T will be equal to? Or let me say it in different words, this delta T will be function of what? Anyone? Change in temperature? Okay, but before change in temperature, don't you think that every beam, like if the beam is steel or aluminum or plastic, they all have different alpha, right? So the first thing that we need to mention in this equation is the alpha, right? You all agree with me in this? So this is the material part in the equation. So I will say alpha. And by definition, alpha is the amount of deformation per unit length and per unit temperature. So what should I multiply this alpha with so I can get this deformation? Anyone? Length and temperature. And the reason why is, let me show you now. So delta T times length. So to get this delta, the deformation, I need to multiply the alpha, which is again the amount of deformation per unit temperature and per unit length. So if I have a 1 temperature and 1 length, multiply by alpha, I'll get delta T. But now I don't have a unit. I have a length of, for example, 10 inches. So I need to multiply this 10 inches with alpha. And then the temperature increased by 50 Celsius, not a unit Celsius. So I need to multiply this by alpha. Is that clear? It's important to understand this alpha, the meaning of that alpha, so that you don't need to memorize like this equation. Okay? Let me tell you something. Again, I'm repeating the definition. The amount of deformation per unit length and per unit temperature. Does that ring a bell in your head? What we mentioned before that has a similar definition? Anyone say strain? Strain. So what is the definition of strain? The amount of deformation per unit length. So let me write that down. So the alpha here is amount of deformation per unit length and per unit temperature. So if I got rid of that part in the definition, will I get that strain here, right? So this is the definition of strain. And this is the definition of a strain. And strain is the amount of deformation per unit length. So to get the strain due to temperature, don't you agree with me that I need to multiply alpha by delta T? Now I got rid of that part in the definition. Now this here is amount of deformation per unit length because I got rid of the per unit temperature by multiplying it by the temperature here. So when I multiply by the temperature, so now I need to multiply this by the deformation to get, by the length to get the delta. So now I can say here, this strain is amount per unit length. Is that clear? So now you understood the definition of alpha and definition of strain T. And of course, if now you know that strain is equal delta L over L, so if I multiplied the strain T now times L, now I have the same, this equation is same as this equation. Right or wrong? Tell me. You have a question?
Yeah.
What?
The first equation?
Yeah.
That's for one dimension, right?
Yeah, that's for one dimension.
We're only going to do one dimension?
In this class, we are only interested in like 1D. Okay. Because this is axial system. I mean, like we are still talking about axial systems, so we are interested in 1D. I think in advanced classes, they might add like another dimensions. Okay? And I think, I didn't look into it, but I think it will have to do with the Poisson's ratio as well. Because once you relate strain in 1D to strain in different dimensions, that's when you add the Poisson's ratio. I don't know the equation, I can look it up, but like I think when you add another dimensions, Poisson's ratio has to be in this equation. Okay? Okay, now let's do some examples on that concept. If I told you how much deflection, and we can say deflection or deformation, both have the same meaning. Okay? So how much deflection does the following bar experience when the temperature decreases by 50 Fahrenheit? So delta T here is equal to what? Negative 50, that's correct. You need to add that negative, okay? And Fahrenheit. And you need to find that the deflection in inches. If you know that alpha is equal to 9.6 times 10 power negative 6, 1 over F, which is 1 over Fahrenheit. Indicate whether it's elongating and shortening as well. Okay, so now if we want to find the deformation, or we want to find the deflection, which is delta. So again, without looking at your notes, what was the delta equal to? Alpha times what? Delta T times L. So alpha here is 9.6 times 10 power negative 6, and the units here is 1 over f. Okay, delta t is minus 50, and the units here is f, and then the length of that beam is 200 foot. But the question asks us to have the deflection or deformation in inches, so I will multiply this by 12 so that I have from feet to inches. Okay? When I multiply this all up, I will get negative 1.152 inches. And again, it's negative, so it is shortening. Is that clear? Easy, huh? It's not that hard. Same question. Same question. What I did add is I had 100 kips here. Okay? Same question. This beam has a temperature decrease by 50, and then I added 100 kips here. So now I want to find the delta. Anyone may guess what the delta here equal to? Okay, same thing, which is delta t times alpha times length. But this is true if this beam was only subjected to temperature. But now that the beam is gonna deform by the effect of the temperature and the effect of what? The axial force of 100 kips, right? So what was the deformation due to axial forces? To add what? That's correct. FL over AE. So now, this is our total deformation. So with this equation, we can find the deformation or the elongation that's going to happen due to the temperature, which is this is the temperature term, and here is FL over AE, which is due to the axial force term. Okay? Okay. Let's take it a little bit. Let's make this a little bit harder by saying that. Okay, I want to close this. By adding gaps. Okay? People in the back, do you hear me? Okay. Just a revision on what we did before. If we had a system like this, what was the compatibility equation that we can derive due to this force and for those two members? If this plate, we did this yesterday, so I believe you are mastering this now. So due to the 50 kilonewton, this plate gonna move to the where? Right or left? To the left, which is your right. And then, what is the relation between member 1 and member 2 now? The deltas. Okay, delta 1 is equal to negative delta 2. Okay? That was easy. Okay, now we're gonna take it a little bit further by saying, okay, you know what? We are adding a gap here. There is a gap here. So here is what should you do in this type of the problems. At the beginning, you will assume, okay, first of all, if the 50 kilonewton was not strong enough to push this plate towards applying compressive on B, I mean, like, the 50 kilonewton wasn't strong enough to take this plate to here. I mean, like, to close the gap and apply compression. If it wasn't strong enough, it will stop somewhere here. If it stopped somewhere here, that means that's a determinant system, right? If I put my hand here, can I find whether this member is tension or compression, right? If I put my hand, what's this member feeling? We put it here, and what's my hand feeling, tension or compression? Tension. That's if the member is determinant. But now, what will happen if the 50 kilonewton was strong enough to close the gap, and not only close the gap, it needs to apply, when it closed the gap, it's going to apply compressive strength because this member got shortened by this amount. Once it's shortened, that means there's a compressive stress there, right? So now, we went back to have this as an indeterminate system, okay? Let me explain it more by saying, okay, now the 50 kilonewton was strong enough to close the gap and apply compressive on 2. Now it is indeterminate system, and this is what we did before, but we will add a very small step. First of all, the equilibrium equation is going to be the same. So if you want to find the equilibrium equation here, we're going to take this plate out. And to take this plate out, we need to cut here and here, at 1 and at 2, right? So the equilibrium equation is going to be the same. But the compatibility equation is going to be different. Let me show you why. So member 1, it was here, then it went to here. So this is delta 1. Okay? And then we have a gap here. This is the gap, and gap gonna be given like, for example, 0.1 inches, okay? And then member 2 got shortened by this amount. Here's the question. What is the relation now between delta 1 and delta 2? Can you see it? What is the relation between delta 1 and delta 2? Okay, wait a minute, let me write it with you. Delta 1 is equal to what? Okay, one minute. Let me put it in different words. The elongation of member 1 gonna be equal to what? The gap plus, okay, that's nice. No, it's okay. Gap plus delta 2. That's correct. But we are missing something. Let me say it. The elongation of 1 is equal to the gap plus the shortening of member 2. So when I mention shortening, what should I add here? Negative. So I will add here a negative, and I will say this negative because of the shortening. I don't know if I wrote shortening right, but you got it, right? So now the equation will be delta 1 is equal to gap minus delta 2, or if I want to put it in terms of delta 1 and delta 2, so delta 1 plus delta 2 equal to the gap. Let's revise what we did before. What we did before was delta 1 is equal to negative delta 2, which if I put it in here, delta 1 plus delta 2 is equal to 0. So previously, we had delta 1 plus delta 2 equal to 0. Now what we are having is delta 1 plus delta 2 is equal to the gap. So whenever now we have, what's called, 1 minute? I think it's called, yeah, whenever we have members in series, you can derive the deformation of member 1, or you can blindly say delta 1 plus delta 2 equal to the gap. That's correct. If there was no gap, now this is the previous lecture. If there is a gap, now delta 1 plus delta 2 equals to the gap. And now you understood how we derive delta 1 plus delta 2 is equal to that constant, which is the gap, right? If you don't need to memorize this. You can just do it like what I did. You see the elongation of 1 is equal to the gap plus the elongation of 2 or the shortening of 2. In our case here, we have a shortening. That's why don't forget to put the negative. Let's make it a little bit harder by giving you this problem. Now, this is not a members in series. Now, this is a coaxial member, okay? So this is some sort of piston. I think so. You can correct me. You're the auto guy here. Okay. I don't know what that is, to be honest. I just found it in the book. So if you have, this is member 2, which is the aluminum part, and this, let me call it brass. Okay. So you have a brass, which is like a cylinder, and then you have a void, and then you have this aluminum, and there is this, I don't know, in the book they call it collar or cellar, I don't know. But you know that there is this guy here, this black guy, and then you have this aluminum, which is gray, and then you have this brass, which is kind of yellow, okay? I just drew it here. So now you just like understood how it's in real life look like. Now let's do it in 2D. So in 2D, what we had this system, and we applied tension here. And this P was strong enough to take member 2, and move it by this amount. And when it applied compression on this brass, it took it also down by delta. Let me show it to you. So the outside system, which is a cylinder, we call it member 1. So this is member 1. And the inside is member 2 with this green thing. And when we apply tension, as you can see, the green thing went from here to here. So let me call this delta 2. Previously, there was a gap. This is our gap. And then we have member 1 here. Member 1, it was here, then it moved to here. You see? Member 1 moved from here to here due to the compression of this member 2. So now I will say this very small deformation here, this is delta 1. Now, whenever I give you any question, you can just, of course, I will give you the deformation before and after, and then I will have you to, for example, conclude what is the relation of delta, which is the compatibility equation, which is necessary to solve the whole indeterminate system. Okay, I need any of you to tell me what is the relation between delta 1 and delta 2. And let me start here by saying, okay, I have now delta 2. So the elongation of delta 2 is equal to what? Anyone? Gap plus delta 1. Or let me say, that's correct. Or let me say it in different words, which is gap plus the elongation of member 1. And once I said elongation, so I will leave it with a positive sign. When it's not elongation, when it's shortening, that's when I add a negative. So the difference between this system and the previous system, that everything here is elongating. So I will add a positive here. So now you can either solve it like this, or you can put it in the previous form, which is delta 2 minus delta 1 is equal to the gap. Is that clear to everyone? Any questions? Okay, cool. So now let's move. So this was hard one. This was very hard, and the previous one was also hard. Now let's go to the examples that we have in the booklet. So we have member 1 and member 2, and then we have a plate in the middle that is getting pushed by 50 kips. Okay? Now I want you to tell me what is the equilibrium equation and compatibility equation. And let me tell you something. We always, at the beginning, like step 1, assume that 50 kips is strong enough to close the gap. So now our system will be something like this. Which is what I think you are used to see from the previous class. Bless you. 50 kip, and then you have member 2, this is member 1, and then I have here. So again, let's review what we did before. So the review here is going to be in the equilibrium part. The new thing here is going to be in the compatibility. So the equilibrium part, whenever you have a system like this, you already know from the beginning it's indeterminate because we have two unknowns here, and we only have one equation in the x direction. Once you know it's indeterminate, I don't want any of you to solve it from the reaction side. I want you to do the cut method, which is whenever you see a plate, just take this plate out, and if we want to take the plate out, we need to make cut in member 1 and member 2. So that will be our box. So I will have, here is member 2, and here is the cut, here is member 1, and here is the cut. And whenever you have a cut, assume that the cut is a joint, and we want to assume our forces is coming outside the joint, and it's drawn this way. I don't want any of you to draw the arrow inside. No, I want you to draw it outside, because that's where you did your cut. And then I had 50 kips here. So summation fx is equal to 0, and then make this arrow and say f1 plus 50 minus f2 is equal to 0. So now this was our first equation. Easy, you did it before, we practiced on this. Now the compatibility part. If you didn't notice that this is a members in series, so we can conclude what is the compatibility equation is. But if you already recognize that member in series, so the compatibility can be delta 1 plus delta 2 equal to the constant or the gap. If you didn't notice this, it's totally fine. You can just conclude it. And how you conclude it? We're going to say the elongation of member 2, for example, is equal to what? Anyone? Don't look at your notes.
Is it gap minus
Yeah. Gap plus the shortening of member 1, which is gap minus member 1. Sorry, delta 1. So now delta 2 plus delta 1 is equal to the gap. Okay? And now, since we only have a 50 kips, so the equation for delta will be FL over AE for member 2 plus FL over AE for member 1 plus the gap. Let me copy this and move it to the next question. So the next question is the same, but now we are adding that the system experiences a temperature increase by 30 Fahrenheit. So our delta T here is positive or negative 30? Positive 30. What's going to change in this equation? Everything going to be the same except that definition of delta 2 and delta 1. So I'm going to move this a little bit, and then I'm going to move the gap a little bit. I need to add to each delta now the effect of the axial force, which was the kips, and then the effect of the temperature change, which is alpha delta T L, and then you have plus alpha delta T L. So this bracket is delta 1, so everything here is 1. And this bracket is delta 2, so everything here is 2. Is that clear? Easy? Kinda? Any questions? Okay. That's nice. I think we're going to leave early today. I think. Okay. Now this is a very hard question, but this is going to explain everything. Okay? So like the hard part of this question is the end of it, because it's very tricky. So it's given here that we have this rod, okay? Everything in this rod has the same area, same everything, but at the end here, we have a gap of 0.2 millimeters, okay? So the question here asks you, okay, determine the reactions at A and B, which is the outside reactions at A and B, if the rod is subjected to 20 kilonewtons, neglect the size of the collar at C, and then the modulus of elasticity is 200 gigapascal. So now, at the beginning of any problem, so now we are asked to get the reactions. But now let's neglect that they ask us about the reaction, and let's get the forces in each member, and I will later tell you what should we do. In the book, they use a different method. They get a reaction, and from the reaction, they solve the problem. But in our case, in this class, what we do the cut method. We take this plate out in the middle, and then we do the equilibrium part. Okay, the first step in these type of problems, what you want to do, okay, I will say, assume that, okay, I'm lazy enough to write, so I'll take a copy from what I wrote before. Where is it? Yeah, here. So I'm going to say assume that the 20 kilonewton is strong enough to close the gap. So now this assumption tells us the gap is closed. So as if we don't see the gap in the equilibrium part. So if we want to solve it, like we want to derive the equilibrium equation, we're going to take this plate in the middle outside, and if we want to take it outside, we want to make a cut in member 2 and member 1. So this will be my box. So this is the plate in the middle. Okay. And here is member 2. And here is member 1. And then I have a force coming out of 2, which is F2. A force coming out of 1, is it 1? And then I have the 20 kilonewtons. Now this is easy. Summation Fx is equal to 0. Then I will say F2 plus 20 minus F1 is equal to 0. I want to make this all in terms of F1, so I will say F1 equal to 20 plus F2. Okay, and this is our first equation. Okay, now the compatibility equation. So what should our equation be? Now, we already said that the gap is closed. So let me start by saying delta 1. So the elongation of delta 1 is equal to what? We are just like deriving it again because we didn't notice that this is a coaxial member. If we did notice that it's a coaxial member, a members in series, we will say delta 1 plus delta 2 equal to the gap. But we didn't notice this. So I will say the elongation of member 1 is equal to the gap plus the shortening of member 2, or the gap minus 2. So I can say delta 1 plus delta 2 is equal to the gap, which is the constant of 0.2 millimeters. Okay? Now I don't have any temperature effect. So the delta equation here, delta 1 and delta 2, both of them will have FL over AE, and the other one is FL over AE. So delta 1 gonna be F1, L1, A1, E1, and then F2, L2, A2, E2, and the whole thing is equal to 0.2 millimeters. Okay? Now let's plug and chug. So F1, I will remove F1 now, and I will put this equation, which is 20 plus F2. So I will say 20 plus F2 times L1, and L1 here is equal to 400 millimeters. Area 1, both of them, they have the same diameter of 10 millimeters, so I will say pi d squared over 4, pi 10 squared over 4, times the modulus of elasticity, which was 200 gigapascal, which is kilonewton millimeter square. And the area here was millimeter square. So I have the same length unit, and the force here, I'm leaving it with kilonewtons so that I know that F2 will come out in kilonewtons. I will say plus F2 times L2. So L2 is 800. Now I have the same area and same modulus of elasticity, so I will copy the denominator and I'll put it down here. And you know from math, if I have an addition and they both have the same denominator, so I can have it as a common, so this plus this over one of them, which is I'm having a common denominator here. Okay? And then the whole thing is equal to 0.2. I will not do any math. I will just plug it in my calculator, and I'm totally fine with this. And I will get F2 is equal to minus 4.05 kilonewton. And then when I plug this back here, I'll get F1 is equal to 15 15.95 kilonewton. Okay? Now, let me ask you a question. Does it make sense that F2 is in compression or no? Why it makes sense? Or what does the negative here tells us? Tell me. It's getting shortening, which means that the 20 kilonewton was strong enough to close the gap, and not only close the gap, apply compression on 2. That's why member 2 turned out to be compressed. However, and this is very important, if F2 turned out to be positive, does that make sense? That doesn't make any sense. And if it doesn't make any sense, means that the 20 kilonewton wasn't strong enough to close the gap. So what came out here is a trash, which we will set directly F2 is equal to 0, and then we have a determinant system. I will show you now in a moment. Stick with me on this. But now let's continue on assumption that, okay, now we had the F2 in negative, which means our first assumption here is correct. Because you don't assume something and like, you need to approve your assumption at the end, right? So you need to return back to the assumption. Tell me. Could F2 equal 0? Can F2 equal to 0? It can be equal to 0, which also tells you that I think it's like barely touching it, so there is no anything. So it's still determinant system. And I will show you now in this next slide. But in this slide, let's focus on that assumption. Our assumption is correct, which is in this case. So what should we do? So I want to draw now an AFD. And this will be an easy AFD because we already have the internal forces, right? So what is the, so I have, this is the system. 1 minute. And here is the plate, and here is the 20. Here is the regions. So the region to the left, which is member 1, what should I draw here? You need to look at those, because this is our internal force. So the internal force in 1 is 15.95 positive. So I'm going to draw positive 15.95. Okay? Member 2 turned out to be negative 4. So I will go down here until I reach to negative 4, and I will close it at 4, 4.05. And this drop is due to the 20 kilonewton that is applied in the question here. From the AFD, can we conclude the reactions or no? So if I want to find the reaction, let me write here reactions. And let's call this is A and this is B. So reaction at A equal to what? 15.95. And how should I draw it? Should I draw it pointing towards A or away from A? Away from A. Anyone has a different opinion? Why should I draw it this way, away from A? Oh, you meant towards A? I mean, like, because look at this again. How can we draw this AFD using our hand? So I'll put my hand at A. What is this 15 trying to do to my hand? Tension. That's why I have intention. That's why I drew it like this. Same way, what should I put in B? What value? First of all, what's the value at B? The reaction? Okay, 4.05. Which direction? Towards B or away from B? Okay, pushing B or pulling B? Pushing B. Not away from B because it's in compression. So I need to draw it like this. 4.05. Does that make sense or no? Because if I put my hand here and I want to draw the AFD, what's my hand feeling? Compression or tension? Compression. And that what the cut method told me here. They told me that F2 turned out to be negative. Is that clear? So now we figured out the reactions, not the book way, but like the cut way, and then we drew the AFD. which I think you all mastered it using the in-class assignment, like the couple problems that we had, and then we turned out to have the reaction. So now we have a complete answer. The next slide here, I will say, okay, what will happen if F2 turned to be positive? Okay? If it turned out to be positive, that doesn't make any sense. And if it doesn't make sense, that means that our assumption is wrong. Okay? And now we do have a determinant system, not indeterminate. I will show you why now. Because if we had this problem and we had 20 kilonewton applied here, and then we have a member 2 here. So this is member 2, and this is member 1, and then we had the fixation here. Now, is this part determinant or indeterminate? Determinant, right? Can all of you draw the AFD for that part? So what's the AFD for that part? So when I put my hand here for member 2, does member 2 feel anything? So member 2 feels 0, right? So you can leave it like this. You can leave it like this, or practically what we used to do, we used to put a 0 here. So this 0 indicates that from here to here, there's no any forces. It's starting from the plate in the middle. What's my hand gonna feel? 20, tension or compression? Tension. So I do have member 1 gonna feel positive 20, which answers your question, what if member 2 turned out to be 0? If member 2 turned out to be 0, that means also the 20 kilonewton applied is not strong enough to close the gap. And now, what we need to answer the question which tells us, okay, you know what? Tell me now, what was the reactions at A and at B? So what's the reaction at A and which direction? $20. Pushing joint A or pulling joint A? Pulling joint A. So this will be the reaction here. And what is the reaction at B? 0. And here's the external force of 20. Let me put it here so that the question now is stable. So the reaction at B is 0. So you can either write 0 here, or what we usually do, we make a line and we make a circle in that line, which indicate that there is no arrow right or left. It's just a 0. Is that clear? Okay. I'm done. I have nothing to say. If you guys don't have any questions, tell me.